Your frontend keeps calling API every few seconds just to check if something changed. That's polling, and it's one of the most inefficient ways to build real-time applications. But what if the server could just push updates instantly without WebSockets? And that's exactly what server-sent events do. In this video, I'll show you how to build real-time event streams in ASP.NET Core and even how to send updates to specific users. Let's start. Normally when browser talks to the backend, the flow is simple. The client sends a request, the server sends a response, and the connection is closed. But with server-sent events, something is slightly different. Here the browser still sends requests to the backend, but the server does not close the response immediately. Instead, it keeps connection open and continuously sends events back to the client over time. So if you have response 1, then you have response 2, and you have response 3. And that's all for the same request. It means that the browser can receive real-time updates without constantly asking the server if something changed. And that's the big idea behind SSE. It's still HTTP, it's still simple, but now the response becomes a stream of events. Let's take a look what actually happens under the hood. Server-sent events are surprisingly simple. When the server returns the response, it sets a special content type, text event stream. So this tells the browser that this is not a normal response that finishes immediately. Instead, the browser should keep listening because the server will continue writing new events into the stream. And each event is usually sent in a very simple text format. For example, you have data event 1, then the next event, data event, and so on. So the server keeps writing into HTTP response stream and the browser keeps listening. And that's why server-sent events feel real-time, even though it's built on top of the HTTP. So no special protocol, no WebSocket handshake, and no extra complexity just to get started. To understand where server-sent events fits, let's compare it to the two things developers usually think about first. With polling, the browser keeps sending requests every few seconds asking, "Oh, do you have new data now?" So that works, but it creates unnecessary traffic, unnecessary requests, and often unnecessary latency. The second option we have is WebSockets. WebSockets creates a bidirectional connection between the client and the server. That means both sides can receive and request data at any time. That's very powerful, but also introduces some complexity. For example, you need connection management, and depending on the setup, scaling may become more involved. So server-sent events sit somewhere in the middle. The client opens the HTTP request and the server continuously pushes updates back. So server-sent events is simpler than WebSockets, more efficient than polling, but it only supports service-to-client communication. And that's actually perfect for many real systems. For example, notifications, order tracking. Now that the concept is clear, let's implement this in .NET Core. I'll start with a simple version of this, a basic stream for order status update. Then after, I'll extend it to more realistic version where events are sent only to the appropriate connected user. Let's go and implement it. Now, before we jump into the implementation, I want to quickly show you something that actually helped me become much better at thinking through technical problems. One thing I realized over time is that good engineers aren't just good at writing code. They are good at thinking through complex problems. And that's exactly why I like Brilliant. Brilliant is an interactive learning platform focused on math, computer science, and logical thinking. Instead of just watching lectures, you'll learn by actively solving problems step by step. They have courses on topics like algorithms, probability, logic, computer science fundamentals, and problem-solving strategies. And what I like the most is that everything is hands-on. You're constantly interacting with the material instead of just passively consuming it. If you want to sharpen your problem-solving skills, you can try Brilliant using the link in the description. The first 200 people who use that link will get 20% off an annual subscription. Alright, now let's build our server-sent event stream in .NET Core. So the first thing we have here is order status update model we are going to use, and it's very simple. We have the order ID, we have the status, and we have the timestamp. And for the order status, we have a couple of statuses. Another thing is order stream service class, which is currently empty. And for the program CS, which is currently empty, we have just added singleton of that service. I'm going to create an endpoint. So app map get, and let's name it orders. It will receive order ID, and let's say this is a stream endpoint. I need order stream service, so I'm going to need a cancellation token. Then I need to subscribe to a stream for that order. In order to subscribe, I'm going to use channel reader or order status update. Let's name it reader, and I'm going to subscribe with order ID. Currently we don't have subscribe method. Let's generate that one, and after that I will return those updates using results server sent events. So we have return results server sent events, where I can say reader read all async. I will pass cancellation token, and let's say this is event type order update. So this is one of the nice things in modern.NET Core. The framework gives us a clean way to return server sent events response without manually formatting everything ourselves. What matters here is that the endpoint returns an anonymous stream of the events, so the browser can keep listening to it in the real time. Okay, now we need to implement subscribe method. So here we will need some dictionary for our streams. Let's use concurrent dictionary. So I will have concurrent dictionary of GUID, which is our order ID, channel of order status update, and let's name it streams. For the subscribe, I will need to create unbound channel. So I will have channel create unbound channel of order status in streams dictionary of order ID. I'm going to store this channel. At the end, I'm going to return channel reader, and let's make it public. Now we have a stream method, which is a subscribe method to our events. Since we have subscribe, let's quickly implement unsubscribe method. Unsubscribe method will accept order ID for which we want to unsubscribe, and we are going to try to remove value from concurrent dictionary for that particular order. Now, to make the demo easier, we're going to implement a simulation. So let's make post method, which will be orders with order ID, and we're going to simulate events. I'm going to accept order ID with order stream service. I will get all statuses, and for each status I want just to delay these tasks, let's say for 2 seconds. And I want to publish this event. I'm going to do that through order stream service. We don't have that method, but we are going to implement it. And for the publish, we are going to use order status update record that we have. At the end, I'm going to unsubscribe, and I'm going to return OK. Let's say order simulation completed. Since this is async method, let's rename it to publish async. I'm going to try to get value for the certain order ID. If I get it, to write to that channel our status update. So points that it loops through different order statuses, waits a little with this task delay, and publishes updates one by one. So this allows us to simulate a real life order life cycle, which is created status, payment confirmed, packed, shipped, out of delivery, and I think delivered, yes. So this is great for the first demo because it shows the streaming behavior very clearly. Let's now test Postman. So the endpoint we have created for simulation is taking ID for the orders and simulate. Let's quickly send this request, and after a couple of seconds we should see order simulation completed. So this was just a simulation, but here's what actually happens in the background. The endpoint starts publishing events. Every 2 seconds, a new order status updated is emitted, and these events will be streamed to the server. At this moment, no client is connected, so nothing is visible. Now let's test this with the real-time part, which is streaming. So for the ID, I'm going to use the same order ID for simulate and for the stream. As you can see, I will send simulate request. I will go to the stream request and I'm going to send stream request. After a couple of seconds, you can see that order update responses are coming. And when you start streaming, you can see that our requests start receiving responses. On every 2 seconds, we have order update response as we set in that endpoint, and it will continue receiving response until we close this connection. So you can see that order ID is exactly order ID we have. User ID for now is empty. We will talk about that a little bit later. And for the status, you can see the statuses are coming one by one in that order with timestamp difference of 2 seconds. If we go and simulate this again, and we will back to stream, you will see again receiving data on that stream because we didn't close the connection. Now this first version is good enough to understand server sent events, but it's still a demo-oriented model. Because in real systems, you often do not want every client to subscribe only by order ID in a naive way. A common follow-up question is, what if I want to send updates only to the correct connected user? For example, user A should receive only their own order updates, or user B should receive only theirs, and maybe an admin dashboard should receive something else entirely. So this is where we move from simple server send events to a more realistic event routing model. So let's go and implement sending messages to a certain connected users. The first thing we need to update here is our order status update, where we need to put our user ID for which is connected the certain order. And for this case, let's use another service and let's name it user order stream service. So now for concurrent dictionary, we are going to use a slightly different approach. I'm going to have concurrent dictionary of string, where string is user ID, and for each user we are going to have concurrent dictionary of all orders, and let's name it user streams. So instead of storing one stream by order ID only, I now keep tracking of active connections per user. So the structure is basically user ID, active connections, channel per connection. And why is this useful? So because a single user may have multiple active browser tabs or multiple active sessions, and each connection gets its own channel. So when an event arrives, I look up the correct user and publish the update only to that user active connections. I'm going to have 3 main options here. Subscribe, so when user connects, I create a new connection ID and a new channel. When update arrives, I send it only to the channel that belong to that specific user. So we have a subscribe method, which is subscription based on a user ID. For the publish async, I'm going to try to get user connections, and for each pair in that connection, I'm going to publish events. Unsubscribe is pretty similar. Okay, now I need 2 more endpoints specifically for user ID. So first, let's expose server sent events endpoint for a specific user. When client connects, I subscribe that user and receive a dedicated connection for that specific user. Then I register cleanup for 2 places. First on the response disposal and the second on request cancellation. So that ensures the connection gets removed whether the streams ends normally or the client disconnects unexpectedly. Finally, I return the events through result server sent event exactly like before. But now the big difference is this: the stream is not just a generic order stream anymore, it is now tied to a specific connected user. And yes, for that purpose I created a helper subscription cleanup, because these server sent events connections can stay open for a long time. This small helper ensures that when the requests end, I unsubscribe the connection safely and only once. It's simple, but it makes the endpoint lifecycle much cleaner. Here is the matching simulation endpoint for the targeted version. This one now includes both the user ID and the order ID. That means every published event clearly says this update belongs to this order and this update belongs to this user. And because the stream service routes by user ID, only the correct connected clients receive it. This is the key difference from the earlier demo version. We are routing them intentionally. Now let's test this case like we tested before. So we have two new endpoints. The first one is user simulate and another one is stream user. So for the user simulate, I'm going to put Stefan as a user and this is the user ID. And for the stream user, I'm going to use the same user and I will stream all the orders for that user. So let's go to user simulate, let's send simulation, let's go to stream user and let's start streaming data and receiving messages. We are already receiving messages for the username Stefan in that particular order, and you can see that I'm still receiving responses for that certain user. What happens if I go to user simulate and instead of this GUID I'm going to receive, let's say, 1 as the last number. I'm going to simulate it. Let's go to stream user and you can see that now for the same user I'm receiving different order, which says to us that this is connected to a specific user, in this case me. Okay, so where is this useful in real life? So I would say in many places. The first one is obvious order tracking. So user sees only the updates for their own order. Another case would be notifications. Each connected user gets only their own notifications or some group notifications. Some dashboards. For example, an internal client receives monitoring or activity streams, admin panels, progress updates, and so on. And all of that can be built with a simple real-time model that then WebSockets when the communication is mainly a server to client direction. So server sent events are one of those features and technologies that many developers just overlook. But in the right scenarios, they can dramatically simplify your architecture. So instead of polling and without the complexity of WebSockets, you can stream updates over the just plain HTTP. And in the ASP.NET Core, the implementation is actually very elegant. So we started with a basic version, then we evolved into a more realistic targeted delivery model, and that already gives you a very strong foundation for real-time backend features. If you want, in the next video I can take a step further and show you how to scale this approach across multiple application instances using Redis or Message Broker. If you enjoyed in this type of .NET content, be sure you subscribe to the channel and I'll see you in the next video. Dream big!